Okay, so thank you, everyone. First of all, I want to thank the organizers, Alexei and the rest of the organizers, for inviting me to participate in this workshop. It's my first SPICE workshop. It's been lovely. Thank you. I don't know if Pyro's still here for the lovely wine yesterday, so I'm hoping it won't be my last SPICE workshop. It's also the first time I'm really interacting with this community on ultrafast antiferromagnet, so I've already learned quite a bit, and I hope to continue the interactions and keep learning more in the future. My name is Ankit DISA. As Thomas said, I was working in Hamburg for several years. Now I'm back in the US. We'll start a group at Cornell in the fall or in the summer. But today what I'm going to be talking about is essentially work that I've done in Hamburg over the last several years in the group of Andrea Cavalieri, where we focus on how to use light to engineer the crystal structure of various materials in new ways, and how we can then use this approach to manipulate magnetic order. And specifically, I'll focus on an experiment that we carried out now a couple of years ago that shows how you can do this to manipulate an antiferromagnet. And if I have time, I'll talk about some new work in a ferromagnetic case, actually. So I probably don't need to motivate this at all in this group. We're all here because we know or we think that antiferromagnets can be much better than ferromagnets for various magnetic technologies. They can be packed more densely. They can be, they're more robust to external perturbations. And most importantly, their magnetic modes are much higher frequency, so they can be in principle switched on faster timescales, right? But the difficulty, and I love this picture from this review article from Thomas Jungwirth, it is shown here where it is difficult essentially to couple two antiferromagnetic materials because of the fact that you cannot use uniform magnetic fields, for example. And in principle, what you would need is some kind of an effective magnetic field that would alternate on each atomic site. Okay, so this is quite impractical to achieve in this particular way. And so I guess what we're all interested in is how we can manipulate order in an antiferromagnet, how we can do this fast, and how we can do this robustly, right? So we've seen already yesterday and today a number of different ways that people have been trying to do this. Electrical control using, for example, current pulses and spin orbit torques, optical control, inverse Faraday effect, magnetic field to terahertz pulses, et cetera. What I will try to argue today is that there is another alternative path, which was already actually introduced by the previous speaker, which is to take advantage of the crystal structure. Okay, and it's based on a very basic and obvious concept, which is that the crystal structure directly determines many of the magnetic parameters that we're interested in the system, right? And so two simple examples, the local symmetry and the crystal field are going to dictate your magnetic anisotropy. And the exchange interactions are essentially functions of the bond lengths and bond angles connecting the different magnetic moments, right? You also have, for example, additional interactions that you can introduce, Jelisch-Kibaria, et cetera, that are dependent on the positions of the various atoms in your crystal structure. So the question that I will try to address is can we take advantage of this strong coupling between the magnetism and the crystal structure to achieve the goal of this conference, which is ultrafast antiferromagnetic writing. And to do that, we developed this approach in Hamburg where we essentially dynamically excite the crystal lattice, dynamically drive the crystal lattice by resonantly exciting vibrational modes of the material with optical pulses. And essentially these are the optical phonons in the material that couple to light. And they have frequencies in the few terahertz to mid-infrared frequency range. Okay, and so what the advantage of this is that you have the ability to really specifically target the atomic motions that you're interested in. The price you have to pay is that you have to now work in this frequency range, which is somewhat difficult to access. So in Hamburg, we spent a lot of time to develop optical sources that can access this frequency range. And now we have the ability to essentially pump the entire frequency range with intense pulses on the order of a few megavolts per centimeter. We don't use a free electron laser, we use tabletop sources, but we can still get to reasonably large electric field intensities at your sample position. And this will correspond to, when you drive the vibrational modes, to atomic displacements on the order of a few percent of the equilibrium bond distances. And these are quite large displacements. And importantly, with these extreme atomic displacements, you enter a regime where the lattice starts to act highly nonlinearly. And you can actually take advantage of this to access specific crystal structures that you're interested in, which can lead to new functionalities, in this case, the magnetic properties that we want to control. Okay, and so this idea of kind of nonlinear phononics, nonlinear control of the lattice was introduced by Andre already, but I want to give a little bit more detail on how this actually works, as it will be important for my talk. So let's try to understand how this works in a simple toy model where we have a crystal structure like this with one single mode. And in this case, what happens when you drive the system with an electric field? We know that we can model phonons as in the material as the atoms in the material as a series of balls and springs. So we have harmonic oscillators, and so we can write down the energy of this system as just a single harmonic oscillator corresponding to the energy of this mode. And this is an infrared active mode, so it's going to couple linearly to the electric field of our laser pulse, right? So in this case, what's going to happen is I'm going to send the electric field onto the laser onto my sample. I'm going to vibrate the atoms corresponding to the phonon displacement coordinate. And essentially, this is a little bit like flicking a ball on a pendulum. I'm going to essentially displace the atoms along this infrared active coordinate. They're going to ring down with some natural frequency and some damping rate. Okay, but the problem is that there is essentially no average change of the lattice when you do this. It's vibrating back and forth at some several terahertz frequencies. And so if we're looking at longer timescales, we won't see any real change to the crystal structure. So we need to do something different. And essentially, when you increase the strength of your electric field pulse and drive the modes to larger amplitude, you can get additional terms that will help you. And one of the things that will help you is that you can now couple different modes together, as Andre mentioned. And so now let's take a look at what happens if we have not one, but two modes. Again, a little toy system. One is the original one that we were talking about, and another one is this mode that I'm calling QR, which is a Raman active mode, which wouldn't normally couple to the electric field. And let's say it corresponds to this motion of this atom up and down here. So now when I write down the energy of my lattice, I'll have the two harmonic oscillator terms corresponding to these two phonon modes. And the lowest order coupling term between these two that's allowed by symmetry is this one right here, which couples the square of the QIR phonon to this QR phonon. And so what that means is that when I shine now my laser pulse, which is now bigger, and I excite this QIR mode to large amplitudes, you're going to vibrate that mode back and forth. But in addition, through this term, you're going to change the potential corresponding to the QR mode. So this is the original potential. And now when I've excited this QR mode, this potential gets displaced. And that means that you're going to now have a lattice that is displaced with respect to the equilibrium coordinate. So we'll look something like this. And importantly, this is directional. This is related to QIR squared. So it only pushes you in one direction. And so you have a net displacement or an average change in the crystal structure, which doesn't necessarily vibrate back and forth. And this is the real key to how this approach works. And so you can see how this looks in the time domain by writing the equations of motion from those from the energies that I wrote down. In red is the equation of motion for the infrared active mode that I excite with light. As you see, it just vibrates back and forth. And in blue, I'm showing you the equation of motion for the coupled QIR mode, which is driven by this QIR squared. And you can see that basically, while this thing is ringing, you're going to get this displacement of this QR mode. And so what you can think of happening in this intermediate time regime here, while this QR mode is ringing, is that you have a new crystal structure. And as I've mentioned before, this new crystal structure can then obviously have different magnetic interactions. And so this is what we can try to take advantage of to control the magnetic properties and achieve switching. And so, the question that I'll ask is, I'll address here in this experiment that I'll show you is how we can use this effect to control the magnetic state in an antiferromagnet. Okay, so the model system that we use to do that is a very simple antiferromagnet, which I think hasn't been discussed so far, cobalt fluoride, but it's a very old antiferromagnet that's been studied since the 50s, really. It has an AL temperature of 38 Kelvin, and it has a rutile crystal structure, and it's formed of a BCC lattice of cobalt ions that you can see here. Each cobalt is surrounded by 6 fluorine ions. It's an octahedron of 6 fluorine ions. Now, in the antiferromagnetic state, what you have is that the cobalt in the center of this cube has a magnetic moment, which is equal in magnitude and opposite direction to the one in the corner. So it's really a fully compensated C-axis antiferromagnet. But the reason that we are interested in this particular material for demonstrating this kind of phononic control is that it has a very unique property, which is that if you apply a strain to the material along the 110 direction, so in this in-plane diagonal direction, you will actually be able to decompensate the two sublattices. One of the magnetic moments gets bigger, the other one gets smaller, essentially turning this into kind of a ferromagnetic state with a net magnetization now, which is going to be linearly proportional to the stress that you apply. Okay, and this is the piezomagnetic effect, which is exactly analogous to the piezoelectric effect, and this is allowed in antiferromagnets of certain symmetries that don't break time reversal, but break combinations of time reversal and some other crystallographic symmetries. And this is one of the simplest piezomagnets that you can imagine. And so, we want to understand how we can take advantage of this using phonons. So let's try to understand what is the origin of this piezomagnetic effect in cobalt fluoride. And that's easiest to understand from the top view. So now we're just projecting onto the AV plane. And what I think is the key to understand here is that here we have a cobalt, which is in the D7 electronic configuration, and the orbital moment here is not quenched. Okay, and that's key because the orbital moment is essentially then going to be related to how split the T2G levels of this of the cobalt are, which is related very closely to obviously to the crystal field and to the bond lengths in this material. And so, roughly speaking, the orbital moment at the end of the day is proportional to the in-plane cobalt fluorine bond length that you have in this material. In equilibrium, the two sublattices have the same in-plane cobalt fluorine bond length, D. So you have the same orbital moment here and here. So you have this compensated antiferromagnetic structure. Now what happens when you strain the material is that one of the bond lengths gets longer and the other one gets shorter, right? So the crystal field changes in such a way that one of the moments, then the orbital moment gets bigger on one side, smaller on the other side. This is what the origin of this decompensation is. Okay, and so this is what is giving you the piezomagnetic effect. And this is quite a useful possible mechanism. It's not the same as switching between domains, but you can imagine this as a way of controlling the magnetic state of the antiferromagnet in two different directions. You can control both the magnitude and the direction of the magnetization by strain. But of course, it has a number of downsides, which is that you have to physically apply a strain, so you're limited to how much you can do before the crystal breaks. And of course, it's also will be slow, going to be limited by acoustic timescale. Okay, so the question is, how can we overcome this? And can we do this by driving the crystal structure with light? And as I'll show you, we can. But what we need to do is find a way to recreate the essential atomic distortions that are driving this particular effect, which is the antisymmetric distortions of these in-plane cobalt fluorine bond lengths, right? And so to get a clue on how we can do that, we can look at the piezomagnetic tensor in this material, which is shown here. The element that we're most interested in is this one, 3,6, which tells you get a C-axis magnetization when you apply an in-plane XY strain. And this particular term is related to the B2, has a B2G symmetry with respect to the lattice, okay? And so what we can do is then look to see what kind of modes we have in this material and see if we have something similar. And in fact, there is a B2G Raman mode in this material. And if you stare at what the atomic motions are associated with this phonon, you can see that indeed one of the bond lengths gets shorter, one gets longer, just like with strain, but this is an optical phonon. So you preserve the volume of the unit cell, and so you won't be limited by all the elastic constraints that you had before, okay? And so in this case, what we would expect is that if we can displace this Raman mode, we would have a magnetization that is proportional to the displacement. But there's a catch, which is that somehow we need to excite a mode that breaks the underlying symmetry of the lattice. Okay, so how do we do that? If we look back at this nonlinear coupling that I talked about before between these two modes, QIR squared QR, we can try to imagine what will happen in this case. I'll excite, let's say, a single infrared active mode in this material like this. What happens here is the problem is that you can only use this mechanism to couple to fully symmetric modes. Okay, what I will couple to in this case is a Raman mode that actually increases or decreases the bond length in the same way on the two sublattices. So this is not going to be something that I can use to generate the magnetization. So instead, what we have to do is actually use 3 phonons instead of 2. Okay, and we can use this 3 phonon interaction, which is more general, where we have 2 infrared active modes that couple to this Raman mode. And by symmetry, we can stare at the group theory tables of this and show that if we have two infrared active modes of EU symmetry, so they're degenerate modes, but one pointing along the A axis, one pointing along the B axis, and we excite both of these simultaneously, we will then couple preferentially to this Raman mode with B2G symmetry. Okay, and so essentially, in order to be able to realize this mechanism, I need to simultaneously excite two infrared active phonons with this symmetry in order to generate the magnetization. And just, I like to show this kind of animation just to show you what it really will look like optically when this is happening. So here's the same crystal, I'm sending in my optical pulse. And what's happening is I'm exciting these two infrared active modes, they're shaking back and forth, but you can see also that you have this displacement of these bond lengths that kind of extends over the whole length of this excitation. So that's what the thing will look like in practice. In order to do this excitation, we need to figure out which modes we can pump. Here's the optical, the phonon spectrum of cobalt fluoride along the two axes. You have these three possible modes you can choose from. They're all three EU modes. You can use then DFT to calculate which ones will have the strongest coupling to this QR mode that we're interested in. And it's this one at 12 terahertz. Okay, so essentially now we just carry out a simple pump probe experiment where we pump these two modes with two resonant terahertz pulses, and we probe using the Faraday effect to track the magnetization dynamics. In practice, two orthogonal infrared active modes, or two orthogonal terahertz pulses, is the same as essentially a linear pulse that can be oriented along some direction. So this is actually, we actually use in practice a single terahertz pulse, which is oriented along the 110 axis to excite both of those modes simultaneously. And so this is the experiment that we carry out. And when we do that, this is what we see. So here I'm showing you the trace of the Faraday rotation angle as a function of time. The pump pulse comes here at 0. Before 0, you can see that there's no rotation, as you would expect in this compensated antiferromagnet. And then when the pulse comes, you see this small increase, and then it decays over the time scale of a few picoseconds. So that's interesting, but it's actually not the whole story. What actually happens if you look on longer time scales is that the signal crosses through 0 and gets much, much, much bigger, and reaches a maximum after a few hundreds of picoseconds. And this is actually the magnetic signal that we're interested in. And here is just a coherent artifact corresponding with the excitation of these phonons. And you can verify this in a number of different ways. For example, we carried out the same experiment on zinc fluoride, which is non-magnetic, but has basically the same phonon spectrum. And you can see that you have this coherent artifact, but no real long-term signal like this. We also carried out a circular dichroism experiment, which shows the same behavior in cobalt fluoride. So this long-term signal is a signature of this pump-induced magnetization. And now we can look at what happens as a function of temperature when we excite this, going from, let's say, 4 Kelvin up to 100 Kelvin. Remember, the nail temperature is 38 Kelvin. And when we plot then this sort of saturated value of the rotation angle or the circular dichroism, we can see that it goes away basically right at the nail temperature. And so and then the temperature dependence, if you look below Tn, follows pretty closely the static piezomagnetic response in cobalt fluoride. So this is somehow a confirmation that we're driving something which is similar to this piezomagnetic effect, but we're doing it dynamically using light and by driving phonons. The other thing that you should be able to do, because with strain you can go in either direction to change the magnetization, is you should be able to do the same thing here optically. And indeed, we can do that by staring at this nonlinear interaction. We can see that if I change the sign of one of these two IR modes, the sign of this force will change. So I'll go from pushing one direction to the other, so we'll flip the sign of the magnetization. And so I can do this by basically changing the polarization of my pump by 90 degrees. Here's the original data that I just showed you. And now if I rotate the pump by 90 degrees, you see that I've flipped the sign of my rotation angle, which means that I've flipped the sign of the magnetization that I've induced. Okay. Now we can also see what happens when I crank up the field strength. I go from, let's say, 1 megavolt per centimeter up to 12, which is the best that we can achieve right now at 12 terahertz. And you can see, first of all, that the maximum rotation angle scales quadratically with the field, which is what we would expect based on the excitation of these two phonon modes. So that's good. We also find that it has a resonance in the wavelength dependence right at the phonon frequency. And so now we can kind of construct a picture of what might be happening in terms of the dynamics and the driving of this particular system. Okay, and so we developed just a very simple phenomenological model. I'm a little bit embarrassed to even show this because it's so simple, but we just expand the free energy in terms of two order parameters, the Néel order vector, and then this induced magnetization. We expand really up to fourth order in every term, but we can simplify this using the fact that we have these constraints of the actual excitation where the induced moment on the two sublattices is equal. And so when you do this, you can just get this very simple form and then write down some simple linearized equations of motion from this particular free energy. And the picture that you end up with is something like this, where you have, in equilibrium, before you drive anything, you just have two, you have the antiferromagnetic order parameter on this axis, the magnetization on this axis, the color gives you the depth of the well. You have the two antiferromagnetic wells corresponding to the two domains of your Néel order vector. And in equilibrium, you have always that the magnetization is sitting at 0. And when you drive this QR mode, essentially what you're going to do is you kind of displace this free energy so that you end up with a net magnetization. This then goes back down at very fast and ends up acting like kind of an impulsive excitation. Okay, and then if you write down and calculate what the dynamics would look like, here's the experiment, here's the theory for the different pulse electric fields, you get very good agreement. Okay, but this is just a very simple model. The other thing that we can do is now we can see what is the potential, what is the strength of this induced moment, right? So if this is something that's very measurable or it could be useful, or if it's just something fun to do in the lab. And so we can convert in a simple way the rotation angle into the induced magnetization and using the magneto-optic constants. And what we get is the maximum that's around 0.2 Bohr magnetons per unit cell. The orbital moment in cobalt fluoride in this case is about 0.5, so it's some significant fraction of that. And so we can compare this now to what can be done with strain. In the previous reports back in the 60s, the largest strain-induced magnetization that was able to be achieved is around 10 to the minus 3 Bohr magnetons per unit cell. So we can achieve obviously something much, much bigger than that. And in fact, if we even looked at what would happen if you stressed it as much as you could before the crystal broke, you'll get around 10 to the minus 5 times 10 to the minus 2 Bohr magnetons per unit cell. So we're actually at a situation where we're almost 100 times more than what you could actually achieve statically. So this is just a fact. This is just a consequence of the fact that we're not really applying strain, but we're doing this dynamically by driving phonons. And this would be equivalent to applying something like a 50 gigapascals uniaxial stress to the system. So something that can be in principle quite useful. Let's see where we are with time. Okay, so I'm almost out of time, but this still leads to a number of open questions, right? So we were able to show that you can use specific, you can drive specific crystal structural distortions by tuning and targeting specific optical phonons. So that's very exciting, but there are a lot of different problems and open questions that it's obviously not ready for prime time yet. For example, as you said, the dynamics were very slow. We're seeing something that's growing on around 100 picosecond timescale. This is something we don't really understand. And so we'd like to, one of the open questions is why is it so slow and how could we possibly speed up the effect so we can get to ultra fast? Another question, which was already brought up earlier today, which is what's happening to the angular momentum here? These are linearly polarized phonons that were exciting. So where is the angular momentum coming from? Still an open question, we don't know. And we have a very simple phenomenological model to describe this, this dynamics, which is based on sort of a longitudinal magnetic moment type of excitation. And so we want to be able to more accurately describe this microscopically speaking, which we don't have a good way of doing right now. So this is where we're at the moment with this. Before I wrap up, I wanted to flash a couple of things that we're doing now just to show you the power of this approach. This is in a ferromagnet. I'm not going to go through the details here, but what we show in the end, this is in a ferromagnet yttrium titanate. And what we showed in the end here, in this case, is that you can actually excite different phonons and you can get lots of different effects. So I'm just showing you the induced magnetization that we get in this particular material after we excite different phonons. And you can see that, for example, you can decrease the magnetization, you can increase the magnetization, you can even increase the effective transition temperature, in this case, up to a factor of 3 by choosing the right phonon excitations, which couple to magnetism in specific ways, right? So this is just to give you the idea, and the take-home message being that driving the crystal lattice with light and doing it in a very targeted way gives you a very powerful tool to control magnetic order, induce non-equilibrium functionalities, potentially in the future, perhaps achieve ultra-fast antiferromagnetic switching. Okay, so that's the take-home message. I want to thank some of the people that worked on this, especially the samples and theoretical support from Paolo Radaelli, Michel Fechner at the Max Planck Institute. And the final thing I want to do is give an advertisement. So I said I'm moving to Cornell in July. And so if there are any postdocs or students or people who are potentially postdocs and students out there who are interested in this kind of work, please don't hesitate to contact me. Okay, so thank you very much for your attention.